states. I mean, I guess it's I mean, maybe semantics on how you define distinguishability, right? So in the sense that, you know, if you have non-orthogonal states, you don't have a 100% way to discriminate those states, because there's some, you know.
There you go. I mean, I don't, yeah, the mathematics seems pretty clear. You could,
Well, so wouldn't you expect that would introduce error in your signal?
you show me where. I mean, you know, that's handling. I mean, look, I mean, I could have two different states. What is alpha and beta? They are like the square root of the mean number of photons in the signal and the phase, e to the I phase. Well, I could have, I mean, I could certainly tell the difference. I mean, this, what's
Well,
here?
but you know, what measurement do you need to perform to tell the difference? You know, the less orthogonal they are, the more measurement you know. I mean, then you're unable to. The less orthogonal they are, the harder it is to distinguish.
I've given a formal argument here. First question is the mathematics correct? Did I make some kind of mistake? Is the math so? And if it is correct, if this violates, oh, where's it? It's the question is this term there or not at the receiver? Okay, we can certainly set up an experiment to measure that and to change it. I don't see why not. I mean, you know, you're just like, you know, you try to save the traditional wisdom just by.
That answers your question, and there is an experiment you could do.
Oh, yeah, no, I'm not disagreeing that you couldn't do an experiment, but I'm just wondering.
Well, the question is this equation correct or not? And if it is correct, it's a revolution in physics.
Those alpha and beta are states of the sender?
Yeah, there's a sender. Alice is the sender, Bob is the receiver. So alpha and beta are two different coherent states. It's a superposition. It's an entangled state. Okay, so the laser is in a superposition of alpha and beta, but it's entangled with a qubit at the receiver. You know, they're created in some common source and they're sent out. You know, there's a laser. I mean, you have to. I mean, this is a well-defined state in quantum mechanics, and presumably, unless there's some kind of super selection where you can't prepare such a state, but there are plenty of publications in the literature on entangling coherent states, Glauber states. And by the way, I've only entangled a Glauber coherent state with a single qubit. You still get the effect if I can entangle two coherent, you know, there could be coherent Glauber states at the receiver and the sender, and the effect is even stronger. And there are papers of experiments where they actually do that. You just look up.
I think we probably need to move on.
All right.
And you?